Welcome, everyone. Let's get started. We have a fantastic speaker with us, and we are going live now on Facebook, and of course, you are here with us in the. I'm going to mute everyone for now, and you have the opportunity to post a question in the chat, and that's something where we can have some interaction. In any case, you want to speak, you can raise hand, and we can go by one and pose questions to our speaker. So first of all, let's get started. We are STEMatters. STEMatters is a nonprofit registered in state of Texas. Our goal is to inspire students at all levels, from elementary to graduate students, even postdocs, to excel in science, technology, engineering, and environment matters, and as well as mathematics. What we do is we bring them together to nurture critical and analytical thinking skills. So the organization engages, guides, and enables students from all over the world to innovate, to invent and deliver high quality solutions to the challenges of our times. And of course, we are every day there are new challenges coming up, especially when we talk about healthcare or extending the boundaries of where we live, going out in space. And that's something which is very relevant to the speaker today. So STEMatters develops research and educational programs to provide local, regional, national, and global activities to learn from each other, to collaborate and compete for excellent outcomes. So we are inspired by many outstanding scientists like Dr. Yarjan A Samad, who is our speaker today. Many such scientists, engineers, doctors, educators, and researchers help us as mentors to accomplish our goals. During the whole year, we run outreach seminars and engagement programs like one today. In summer especially, we run summer camp programs also. STEMatters doesn't have any full-time employees, but we are a bunch of volunteers who are doing this from around the world. So now focusing on today's talk. So today we have an accomplished scientist, Dr. Yarjan A Samad. He and I, we go probably 8 years back when he was a student in UAE. That's when I was invited there to give a talk. And so we have followed each other, seeing amazing work. But of course, Abdul Samad has done amazing work. So he's a senior research scientist and a teaching faculty at Cambridge Graphene Center. He's the first space scientist from Pakistan at the Cambridge doing space work and space application. He has won many awards for his work. He's mentoring many students at different levels, especially graduate student, master, and PhD. And his work stems from his hard work, which spans many continents. So during his PhD work, he worked at top institutions in Japan, in the USA, and China. And that has helped him have a perspective on what is happening all over the world, and especially applying it to his current work. So a little bit about STEMatters again. So we do many activities. Please subscribe, like, and push that red bell button on our YouTube channel. I will share these links in the chat as well, where you can just copy paste and become part of what we do. And that will help us reach out more to you and bring more programs to you. So now let's get to our speaker and let's hear some amazing work that he's doing. All right, thank you, Dr. Yarjan, and this is now over to you.
Thank you, Professor Samir, for the very humbling introduction. And I welcome you all on this talk. The topic today is based on composite materials, especially graphene-based composites and some of their applications, which include these best applications, among others. But before I go to my talk, I'd like to introduce you to my foundation, which is in my name. And the aim of the foundation is basically enhancing the quality of education in Balochistan, especially the primary education for now. And we are introducing new mode of education and new systems of education in Balochistan, which we call problem-based learning and also project-based learning. It's similar to the Scandinavian learning system. We are also building collaborations. For example, the Astronova school in built by Elon Musk in Los Angeles. So they're trying some new learning methods, for example, experimental learning, and we are trying to do the same in Balochistan. You can follow the page of our foundation on Facebook, LinkedIn, and Instagram for more information on the foundation and the school that we are trying, schools actually, that we are trying to build. So the first school of the foundation we are building is in Buleda, which is my village. It's in south part of Balochistan. It's a town, village town, you can say, in the southmost part of Pakistan. It's right at the border between Iran and Pakistan. It's an arid region. It has some sort of agriculture related to date farming, and also it is archaeologically rich. You can see many archaeological sites in Buleda, but in general, it's very underdeveloped and has a lot of date palm trees, which is the symbol of Buleda, you can say. So this is the school that we are building. It's almost complete. We have got about 29 to 30 rooms in this school, and we are trying our best to put it up and running soon. And we will update on our foundation pages on any update on the school. Okay, so with that, I come to the main part of the talk today, which is talking about the materials, and we are talking about composites. So first of all, why are we talking about composites? And then I'll move on to graphene-based textile composites and their applications, and graphene-based foam composites and their applications in space, and some future outlook. What are we looking at, and what are we trying to do in future with graphene and graphene-based composites? And if you have any questions during my talk, you're welcome to ask. You can type the questions in the chat, and I'd love to interact with you guys during the talk as well. So we're talking about composites. Composites is a material which is a mixture of two materials. One is called reinforcement, and another is called the matrix. The reinforcement usually is the harder or the stronger part, which holds the matrix together, and the entire thing is called a composite. You can relate it to like the mud making process, or the mud blocks, which are made by combining straw with the mud, and then to reinforce the mud, and that's actually a composite material. Nature has a lot of composite materials as well, and wood is one of them. So wood is a natural composite which has all the ingredients of a composite material, and it has got the strength as well. As we know, bone, a human bone, is a composite material. It's kind of a ceramic-based composite material, which is found in nature. There are many other composite materials in nature. For example, you can take, for example, these sea sponges, which are made of glass fibers. So the nature makes glass at the seabed. And these are formed in the form of a composite. So these are some natural composite materials. Besides that, if you look at the history of composite materials, you might have heard about Mehergad, which is an archaeological site in Balochistan. It's in Sibi, and it's as old as perhaps 9,000 years, and we have mud-made houses there, which are an example of what a composite material is. So we have historical data on like the people in the old ages had an idea of making composite materials in their own way, and they were using them to build their houses and other things. For example, even the wooden bows and arrows made in those eras. Similarly, the Great Wall of China, there are bamboo-based concrete composites which were made at that time when the Chinese Great Wall was made. And similarly, there are so many other historical figures and places which are full of concrete-based composite materials as old as 2,000, 3,000 years. So the composite materials around us today, we see stealth-based composites which protect the aircraft from radars. We see carbon. We see. I think somebody's mic is on. If you can just mute it, please.
Let me take care of that. Yeah, sorry about that.
Yeah. Okay, so then we have carbon fiber-based composite materials used in the aircraft as well as cars. And we also have glass fiber-based composites used in for example, boats. So there are so many other applications of composite. For example, the tires are made of rubber with reinforced. Sorry. Okay. No, excuse me. Can you see the screen well, Professor Samir? Can you see my screen? Can you hear me?
I can see your screen. Yeah.
Okay. So there was a problem. Okay. So one of the examples of composite materials also the tire, which are made of sometimes reinforced with rubber, reinforced with metallic.
You're not in the presentation mode here. You are showing.
Really?
Yeah.
Okay. So let me check.
It's showing the added mode.
There is some problem.
So you have to get into the presentation mode, and that should be okay.
Yes, I actually went into the presentation mode, but check. Perhaps now?
It's still in the edit mode.
Really?
Yeah.
I think I need to reshare it again.
Yeah, you can share the screen which has the presentation of the slide in it.
Yes.
Yeah, this one is good. Yeah, now we are there.
Okay.
Yeah, we're good.
Okay, there is some
No, it
problem
has to again into the edit mode.
Yes, I don't know what is the problem. There is some problem. Okay. Now?
Yeah, it's good now.
Oh.
It went again to the edit mode.
Yes, I don't know what happened exactly, because when I click, it just goes into this mode.
Okay. I think it's okay if you can work on the edit mode as well. That's fine. So you can swap in the presenter view.
Yes, now?
So, yeah, it's okay. But if you click on it, there is a swap button. But yeah, we are seeing your slide now.
Now it's okay, right? So
now
it's in
okay.
presentation mode.
Yeah, it is.
Okay, that's good. So yeah, we were talking about the tires, which are also an example of composite materials. But when we talk about research, we always look at the roadmap where we want to be, let's say, 5 years from now, 15 years from now, 20 years from now. If you look at the composite materials roadmap of the aerospace industry, the aerospace industry is looking into, for example, from 10 to 15 years from now, the aerospace industry is looking for a transformation in the manufacturing as well as the materials production of the aerospace industry. For example, if we look at the history of aerospace, we started with materials such as aluminium, and we went back to composite materials, for example, the carbon fiber, glass fiber, and many other these kind of materials. But today we are talking about graphene and carbon nanotube and particulate or nanoparticle reinforced composite materials. But from now on, the aerospace industry is looking at not only the materials, the cutting edge materials such as graphene and carbon nanotube based composites, but also the combination of additive manufacturing, artificial intelligence, and these cutting edge materials together to give the new products. For example, you can look up the Boeing NSR, which are the aircrafts of future with much enhanced performances. If you look at the roadmap of aerospace industry, there are two main points which are given the most attention, which are the additive manufacturing and graphene, where additive manufacturing has got more votes from the aerospace partners such as Airbus and many other aerospace or aircraft building companies, but they are actually interrelated. So the graphene-based composites can be made using additive manufacturing, or the CNT-based composites can be made using additive manufacturing. The point here is that we are looking at a future where graphene-based composites would play the most important role among the materials of the future in aerospace industry. And graphene-based composites, along with additive manufacturing assisted by quantum technology, artificial intelligence, and machine learning. So this is the combination that we're looking at for the future of the aerospace industry. Similarly, the automotive industry is also working hard towards bringing graphene-based composites into their production line. And in fact, we have some collaborations with some companies. Take, for example, Fiat, where we are pushing graphene-based composites into their factory floors. The automotive industry is interested so much in the graphene and the introduction of graphene in their production line that there's a conference dedicated to graphene in automotive, which is taking place for the third time this year. So we're talking about graphene. So what is graphene? Graphene is basically an allotrope of carbon. It is the stack of carbon sheets on top of each other. If you look at the graphite is basically this kind of a structure where sheets of carbon atoms are stacked together with some weak van der Waals forces, and these weak van der Waals forces can be broken, and this sheet can be basically isolated, just like you can isolate a note from a bundle of notes which are bound together, and the binding is weak and it can be separated. And based on this, then this sheet can be used to make graphene, and this is the graphene sheet which basically made Professor Geim and Novoselov win the Nobel Prize in Physics in 2010. Why is graphene important for composite materials? The most important aspect of graphene that we look at for composite materials is its strength. You can imagine the strength of this material from the fact that a saran wrap thick graphene sheet is able to lift an elephant, hypothetically speaking, of course. But the use of graphene for composites only for strength is already old, and now we are looking at the application of graphene for functional properties, for example, for sensing, for thermal properties, for many other things. For example, the superconductivity also in graphene is the talk of the town these days. So among strength, there are so many other properties of graphene which are of interest. Graphene can be produced by many methods, and one of the most important, or one of the basic method, was the mechanical cleavage, in which the graphene sheets are basically mechanically cleaved or mechanically separated from graphite. But this process, as you can imagine, is a very low scale, laboratory scale process, and it cannot be upscaled into the industrial floors. There are many other methods. For example, there is these carbon segregation methods, which are similar to another method called chemical vapor deposition, which makes sheets of graphene with a gas source, such as acetylene or methane gas. But all these procedures are not scalable enough for industrial use. And there is one method, which is ultrasonication, where basically graphite powder is broken into small graphene sheets with the help of ultrasonic waves. This process is close to scalability, or this can be scalable, but then there are many methods that we have invented which are more scalable and industrially more friendly than all the existing methods. So talking about the properties of graphene and its applications. So the application is not only limited to aerospace or automotive, its applications are also in the solar cells, in LEDs, flexible displays, transistors, supercapacitors, among many others. So what do we work on based on graphene and graphene-based composites? First of all, we have introduced at Cambridge Graphene Center, we have introduced a new method of making graphene. It's called the shear exfoliation. We also call it microfluidization or high pressure homogenization, where we use powder of graphite and then we use a machine. It's called high pressure homogenization, which basically has some process which exfoliate the graphite into graphene, and it can make graphene inks for liters and liters and kilograms, which can be scaled to even tons for industrial use. And these are the kind of sheets that you're looking at under the microscope for this graphene. And when we talk about graphene, I wanted to bring to your attention that graphene is, we refer to graphene mostly as a class of material, and the same procedure we use to make other materials which are graphene related material, because they are similar in properties and structure. For example, molybdenum disulfide, hexagonal boron nitride, and so many others, which we make using the same method, which is industrially scalable, to develop these materials as inks, which can be used for manufacturing into composites and many other things. For example, at Cambridge Graphene Center, we have many research areas. Among them are printing of graphene and production of composites, and patterning of these graphene. We use inkjet printing, we use screen printing, flexographic printing, which is used for newspaper printing. Just imagine that instead of printing a newspaper, we can print graphene on top of a paper or any substrate, and which can have functional properties. We also use a spray coating, bar coating, and lithography and biodot printing for these kind of printing of these graphene onto different substrates for a range of applications. Today we are talking about composite materials. So we use these graphene-based inks we produce in very large quantity, and then we extrude it along with a polymer. For example, you can take the polypropylene, amide, and PEEK and polyethylene and many other polymers, you can name it, and we can produce these composites using extrusion. And then we have these graphene-based composites made via an industrially scalable process. then we can use these graphene composites and we can make them into filament reels. So these filament reels can then be used in 3D printing. And this is one of the examples of 3D printed sensor. So this is a 3D printed graphene, which is a pressure sensor, and it has a gauge factor of over 20, which is done by one of our students at Cambridge Graphene Center. So we also use this graphene to make electronic textiles. So I introduced the concept of electronic textile, graphene-based electronic textile in 2013, which has then gained a lot of attention from around the world. So we basically coat any textile, for that matter, with graphene. You can take, for example, polyester, nylon, cotton, wool, Kevlar, glass fibers, you can name it, and we can print or coat these textile with graphene and make them functional. So this is one fiber of nylon under SEM. So this is in situ electron microscopy, where we have nylon fiber without coating of graphene, and this is one with graphene coating. We twist it in microscope and we see whether the graphene detaches or not. As you can see here, that we can twist it to as many as 7 twisting cycles, 1800 degrees, and we still can introduce only a little bit of cracks on this nylon fiber, but the graphene still doesn't detach. So these kind of textiles can be used as pressure sensors. So these textiles are made into composite by combining them with polymers such as PDMS, and then they're used as pressure sensors. So in this case, we have a pressure sensor which can sense as low as about 10 kilopascals of pressure, and then we can do these pressure sensitivity for thousands and thousands of cycles. Here you can see about 6,000 cycles of pressure sensing with these kind of electronic textiles. We have used these textiles as a wristband to measure the blood pressure flowing through our veins. This is the demonstration of sensitivity of these pressure sensors that we have built with graphene-based textile-based composites. We have used such pressure sensors in collaboration with one of our companies, Novalia, and we have made graphene-based shoe soles. And these shoe soles basically are connected via Bluetooth to a gaming platform where we can play games with our foot, because we have graphene-based shoe soles connected to our shoes. And this is one of the demonstrations of the applications of graphene that we are doing. And this is me demonstrating the use of graphene in gaming platforms in the Mobile World Congress 2019. We can also use these textiles for concrete manufacturing as well. So this concrete manufacturing, we have put a graphene textile in inside the concrete, and then we can do force sensing. So you can imagine that there can be a bridge which senses any pressure or any stress on top of it, and it can do self-health monitoring when installed on a bridge or any construction architecture, for that matter. And we can do it for thousands and thousands of cycles. And if we have these kind of concrete installed on a bridge, instead of installing a lot of strain sensors, we can have a bridge which is made of this kind of concrete, which has graphene-based textile inside, and it can do self-sensing without any use of localized strain sensors. Similarly, the textile inside the graphene is inside the concrete, which is the graphene-based electronic textiles, can do toxic gas sensing as well. For example, it can sense NO2 because the graphene is sensitive to gases. It's piezoresistive, and any introduction to gas, the absorption of gas particles on graphene changes its resistance. And we can do gas sensing as well as temperature sensing with these kind of graphene-based concrete composites. We also convert these graphene inks into foams or into 3D structures. And these 3D structures are important for composite applications, especially for space applications. So here you can see that we produce graphene inks, and then we convert them directly into foams. I haven't talked about the foam making procedure in detail, but you can ask if you're interested, and we can talk more about it. And these foams, then we can make composites out of them, and then these composites of foams, so that's how they look like under the microscope. So this is an optical video of these foams from inside. So these foams made into composite can be used for loop heat pipes. So instead of like a steel-based evaporator of a loop heat pipe used for space applications, we can replace it with graphene-based foams. And then this is one of the setup where we have used graphene-based foams for this application for the loop heat pipe. So this is an experimental setup that we have made in collaboration with European Space Agency, Leonardo Microgravity Research Center in Brussels, and CNR in Italy, and also Nord Space in France. And in their collaboration, we have built these experimental setups for testing of graphene-based loop heat pipes in space environment. And these are some of the videos where we are doing experiments in parabolic flights facilitated by the European Space Agency in launched from Bordeaux, France. So this is the results of these experiments where we have used graphene-based foam composites instead of steel as an evaporator in loop heat pipe. So it performs about 3 to 8 times better than a steel-based composite used for the loop heat pipes. So this is another application of graphene that we have launched using our sounding rocket in collaboration with the Swedish Space Center and European Space Agency, where we have tested these kind of graphene-based composite materials in a space environment. I don't have much details to give you at this time about these experiments, but I think we will get these results published, and you'll be able to see what we have done in these experiments launched from Kiruna in Sweden. So this is the kind of work that we are doing now.
We have a question which is about
Yes.
the solvent that you usually make for graphene ink.
Yes, so the solvent is a very important factor in exfoliating graphene. So when you exfoliate the graphene, you may use one solvent. For example, for us, the preferred solvent is water, because water is very easy to deal with. But when you talk about space applications, water is not the safest solvent. So for a space application, we use some other solvents which are recommended to us by the agencies which are working on in the space sector. For example, one of the solvents is hydrofluoroether, HFE, which is used readily in space. So the experiment that I was showing in the last experiment, it is testing of that graphene which we have produced in HFE in the space environment. So HFE is some sort. So my point is that we can produce graphene in any solvent. What happens sometimes is that we can produce graphene in one solvent, and then we have our own method of exchanging the solvent. So we can exchange the solvent from one solvent to the other using a protocol, a procedure that we have built at the Cambridge Graphene Center. So it can be said that almost any solvent is possible. So we can produce graphene, or we can stabilize graphene in almost any solvent. I hope this answers the question. Is there any other question, Professor Samir?
Yeah, so there's another question about the scope of graphene-based composite in EMI shielding, and especially when we are talking about space application, where you have many more radiations which are affecting those. So what can you say something about that? But
I'll talk about this actually, because this is something that we are going to talk about. So there are so many projects that are up upcoming and which we are talking about. And I would like to, ask the audience to think about it as well if they have some interest in graphene-based materials. So in general, the research theme that I adopt is finding the challenging in sectors. For example, for now, the sector that I'm working with mostly is the space sector, but I have worked on energy and healthcare as well. And then using those challenges, employ it to see if my expertise of working on 2D and layered materials such as graphene, whether we can solve those challenges with these materials. And then if we can, then how can we do it? Can we use these materials as it is? Do we need to produce these materials in a different way in order to solve the challenge? For example, I gave you the example of HFE that, for space application, we cannot just put material in any solvent. There has to be some protocols to follow. So we modify the properties of these materials in order to suit the application or in order to suit the challenge that we are trying to solve. And then we go into the final stage of design and manufacturing. So we collaborate with the industry in order to push the applications in the industrial floor so that we are not just doing the blue sky research, but we are trying to push the boundaries and apply these solutions in the industrial floor. So in this regard, we're trying to build some robust 3D structures of graphene for space applications. And we have made so many advances in graphene-based foam-based composite materials where we have produced very high density foams. And these foams have very interesting microstructure because all the microstructure is a very organized microstructure. You can take, for example, the sugar cane. So these kind of forms mimic the microstructure of a sugar cane. That's why they're strong, as well as the properties are also directional. So this is something which we are trying to do. And also there are some evidences that the laser propulsion of graphene is possible in space, such that the graphene can be propelled in space using some laser sources. So this is something that we are really interested in, and whether to use the bulk graphene or the 3D structures or the printed graphene or the graphene composite materials and propel it with using lasers in space. Talking of the EMI shielding, so we are interested in producing suits for the astronauts, and also the materials for space which shield against the radiations. And it is not only the electromagnetic radiations that we are interested to shield against, but also the cosmic waves, the galactic rays that are coming from all over the galaxy, and we don't even know what exactly they are. Sometimes they are metal particles such as manganese or iron. So they come at such high speed that we call them radiations, but they're able to impinge upon and injure anybody in space. So this is something that we are really interested in. These particles are usually ionized. That's why water is a very good protection. But we have some new concept, which I cannot talk about here, where we can combine graphene with some water-based components, where we can do the EMI shielding as well as the shielding from these kind of galactic rays as well. So these are some future applications. And yeah, I did not want to disclose this, but I think I've just written it down here. Okay. So there is a moon mission coming from the Mohammed bin Rashid Space Center, where we are collaborating with them, and we are trying to test graphene in the moon environment as well. So we are installing a lot of composite materials of graphene in this moon rover, which will be launched in 2022 to see the effect of graphene and its interaction with the moon soil and some other experiments. So with that, I thank you all, and I thank a lot of people who have taken part or who have helped or supported this the research, the work that I've done, and also the funding agencies, whether it's the Graphene flagship, or which is funded by the European Union, or the European Research Council, or the EPSRC in the UK. And I especially thank Professor Ferrari, Dr. Carlo Iorio from the Microgravity Research Center in Brussels, among many others, who have always been instrumental in making the work possible that I've just presented to you. So thank you for listening.